Hello, everybody. We're going to talk about the physics of superheroes today, and this is the plan for the whole week, in fact. So we're going to just leap on into it like Superman would. And this unit is called Up, Up, and Away, Superman and Kinematics. This is just a review of all those kinematic equations that we did back in September, where we used constant acceleration and initial velocity and final velocity and time and distance, and we looked at relationships between uh, all of those factors. So here's what you should know about Superman. Well, you already know he is able to leap tall buildings in a single bound, and according to this early Superman comic, he couldn't fly. He hurled himself through the air in 700-foot leaps. So originally, Superman couldn't fly, but he could leap tall buildings in a single bound, like you know. And the explanation for that was he came from a planet with stronger gravity. So he had the genes to be able to jump super high. It's just that here on Earth, there was less gravity, less pull of gravity than existed on Krypton, and so he could leap tall buildings in a single bound because of his mighty thighs. Okay, so knowing what we know of physics, we could make a few assumptions and calculate the acceleration of gravity on Krypton. It's possible, and we're going to do it. Here's how. Here's what you need to know about Superman. The fundamentals are, in an early comic book, they said that he could leap into the sky 1/8 of a mile high, which would be a very tall building back when these were being written. That would be the height of a skyscraper, about 660 feet. Okay, it would be 1/8 of a mile. And here's the conversion. We're going to take these feet into meters, and we're going to take any pounds into kilograms. 1 foot equals 0.305 meters, and your task now is to answer the question, how many meters can Superman jump? Anytime you see this calculate here, this is going to be something I'm asking you to report back to me in the problems on the assignment that I'll post on Wednesday. So here it is. Calculate how many meters can Superman jump. You can pause here if you want to, or just swing around back to it. Next, we need to know Superman's initial velocity. There he is, by the way. This is after he is done leaping over this building. Superman's initial velocity. Here's what we know about Superman's leap. This looks like kinematic equations. We don't know how long the leap took, how many seconds. We know that after he left the ground, his acceleration was negative 9.81 meters per second squared because he was stuck obeying the laws of physics. Now that he can fly, he doesn't have to obey the laws of physics. But early on, he was stuck, just like you and me, with all those kinematic equations and had to abide by those. So that's his acceleration. His final velocity in a straight up and down jump was 0 meters per second. We're talking about just the leap up. So if he's leaping up this building, his final velocity is right here. He stops moving vertically and then comes straight back down. So we're just assuming he does some show off. He leaps straight up into the air and comes straight back down. And his final velocity right here at the top would be 0 meters per second. The height of the building was 660 feet, and you calculated that in meters. We're going to use that. And then the initial velocity, that's what we want to calculate. What was that initial velocity? So there's an equation that can relate all those things. Good news. Here it is. Vf squared equals Vi squared plus 2a delta x. So final velocity squared equals initial velocity squared plus 2 times acceleration of gravity times the change in position, okay, the height of the building. So we're going to do a little algebra on this equation, and we'll subtract 2ax from both sides, and it becomes Vi squared equals Vf squared minus 2ax. But you know that Vf is 0, so that term just goes away. So here's what we're left with. Vi squared, or initial velocity, how fast Superman is going the instant he leaves the ground, minus 2 times the acceleration of gravity times the change in elevation, or the height of that building in meters. Now, calculate. What is V sub I? Superman's initial velocity. My coworker here needs me to let him outside so he can go pee in the front yard. I will be right back while you're calculating. Okay, we're back. So we've done all this. There's the equation. Now, so you know the initial velocity of Superman the instant he leaves the ground, and we're going to try to walk from there to the acceleration of gravity on Krypton. Here are the steps we're going to take. We need to know the force that Superman applies to the ground. You'll see why soon. So that's important. What's the force that Superman applies to the ground when he pushes off? And here's the equation we're going to use to do that. Force equals mass times acceleration. And acceleration, so there are two formulas we're going to dig into a little bit here. Acceleration equals the change in velocity, delta V, divided by time, or change in time, I guess, technically. But we'll live with it the way it's written. So to get there, force equals mass times acceleration. We need to know Superman's mass. I'm just going to eyeball him and say that he probably weighs 220 pounds. We don't like to use pounds in the physics classroom, so 1 kilogram equals 2.2 pounds. What is Superman's mass in kilograms? Calculate that. Now, there's the other equation. Acceleration equals delta V divided by T. Here's what we're talking about in this equation. I'm not talking about the acceleration of gravity because we know what that is. I'm talking about how much does Superman accelerate in the act of jumping. Okay, so just in the act of bending his knees and then leaping into the sky. So that's the question. So change in delta V equals change in velocity equals final velocity minus initial velocity. Final velocity is that number you calculated before. It's the final velocity of the act of leaping, of the act of pushing off the ground, is the initial velocity of his actual flight through the air. Okay, so that number you calculated in meters per second for V sub I, as he leaps up and over the building, that's his V sub F for his push off the ground. His initial velocity on the push off the ground is 0 meters per second. Initially, he's just squatted there with his knees bent at 0 meters per second, and then he launches himself. How the T, we're just going to assume that it takes him a quarter of a second, 0.25 seconds, to straighten his knees up, swing his arms, and leap into the sky. So here's what you're going to calculate now. What is Superman's acceleration? It's delta V, or V sub F minus V sub I, divided by 0.25 seconds, divided by T. That's it. Next. Okay, so getting from V sub I to acceleration of gravity, we need to know the force that Superman applies to the ground. There's the equation. We know Superman's mass. You have just calculated the acceleration of his leap. What is the force that Superman applies to the ground? That is his mass times that acceleration that you just calculated. Here's your next calculation. Calculate force here. Next. Okay. That force that Superman could apply with his mighty legs, he could apply on Earth or he could apply on Krypton. It's the same force. So let's assume that that force is 70% more than what he normally applies just by standing on Krypton. So on Krypton, the force of gravity is stronger, the acceleration of gravity is stronger, so he could jump, but he would just be like a normal dude on Krypton, and so if he jumps in the sky, he's just going to look like me, probably a little better than, probably a lot better than I, but he's just going to look like a normal person jumping in the sky. So this is, that 70% is a rough calculation, assuming that when people jump up into the air, that is more than they're applying a greater force to the ground than the force that they do when they're just normally standing. Okay, and you could do this if you stood on a bathroom scale and you just weighed yourself. What you're weighing is a force, and then you had someone watch while you jumped, and you would see that needle leap up as you jumped, as you pushed off. Okay, so we're assuming that the spike in the needle is about 70% higher than what's normally than your normal force of gravity applied to you. Okay, so the force of gravity on Superman on Krypton is the force you calculated divided by 1.7. So you calculated the force that he pushed off the ground. The force of gravity on Superman on Krypton is that force divided by 1.7. Calculate what's the force of gravity on Superman on Krypton. So that's just the force you calculated earlier divided by 1.7. Getting close, guys. Now, back to this. Force equals mass times acceleration. Now, so you calculated the force of gravity on Superman while he's on Krypton in the previous slide. You calculated Superman's mass in kilograms. Now, we're going to use this equation to calculate the acceleration of gravity on Krypton. Except we need A by itself, so we'll divide both sides by m, and you get acceleration of gravity on Krypton equals force divided by m. Calculate what is the acceleration of gravity on Krypton. That's the thing we're driving at. If you do this calculation and you get an answer that's less than 9.81 meters per second squared, you tripped somewhere along the way. You're still a good person, but your physics didn't follow through. So we're going to take this step by step. If you have questions, you can email or talk with me on Tuesday or Friday about this. All righty? Go be awesome.